before we start trying to avoid cache misses, it's useful to see which kinds of cache misses there are, because there are different methods to avoid the different kinds. So first, compulsory misses. They are also called cold misses, and they are cache misses due to the CPU has not, or the program has not accessed this data before. How can we avoid them? Well, usually they are not a big concern because they only happen once, obviously, but if they are, they can be avoided by prefetching the data before it is needed. We will come to prefetching later. Capacity misses, they are misses due to the cache is too small. So we simply access more data than fits the cache. And what can we do about that? Try to use a different data structure can help. We will look at ways to do that. Conflict misses. That is related to something called associativity. And I will not talk about that in this course, but it's in the efficiency course instead. Okay, so it's not of primary concern for, it's for both uniprocessors and multicores, but I will take it in the other course. It's in the other course. Okay, but in parallel programs with shared memory, there are two more kinds of misses, and they are called true sharing misses and false sharing misses. And what they mean is that a true sharing miss, it's a cache miss that is essential in the sense that if the CPU would just ignore it, the program wouldn't work. False sharing miss, on the other hand, if the CPU or cache system could just classify this cache miss as a false sharing miss, or it could simply ignore it, and the program would still work exactly as if it would see the miss. So these are non-essential, and it's not only that they produce cache misses and delays. I mean, they are cache misses, but they produce delays. But one can also measure the network traffic due to these misses. So these are essential cache misses and result in essential network traffic, while the false sharing misses, they perhaps should be avoided. Okay, and why are there false sharing misses? Well, basically it is that the cache block size is larger than one word, or 1 byte, or one int, size of one int, or one double. The reason is that the CPU fetches more data than it actually needs to exploit spatial locality. Okay, so that means it fetches data that some other CPU may want to modify, but that data is not related to what the current CPU is working on. Okay, so to avoid all false sharing misses, it would be sufficient to fetch only one word at a time, and then only the compulsory, capacity, conflict, and true sharing misses would remain. But to exploit spatial locality, we accept some amount of false sharing. So here is an example of a false sharing miss. Say this CPU, well, first of all, these two words 0 and 1, they belong to the same cache block. And the first time here, it gets a code miss, and it loads both word 0 and word 1. Okay, and then the CPU 2 loads word 1 and modifies it. That means invalidating the cache block from processor 1. But now processor 1 wants to read that word again, and it's not present in its cache since it was invalidated, and therefore it's a well, not yet, we don't know yet what it is, but if this is the complete program, we can conclude that it's a fault sharing miss because processor 1 didn't read any new information, so it could have been just ignored. So how can we know that the cache miss is a true sharing miss? If we look at the same program again, but add one more instruction, and then at this point it is a true sharing miss, but it's not yet known that it is a true sharing miss because, well, if this word, I mean, if we would have fetched word 1, then it clearly would have been a true sharing miss, but we didn't. But we can look at the cache block as having a lifetime in the cache. So from it was fetched until it is removed for some reason, such as being invalidated or overwritten by some other data. During that lifetime, if the CPU accesses any new word, then it was a true sharing miss. Okay. As a curiosity, for you who are from LTH, I mean Lund University, the correct classification of true versus false sharing misses was done in the e-building. I mean, to the algorithm for doing that, it was done in the e-building when Professor Michel Dubois was on sabbatical at the Lund University in 1992. Okay. Two previous studies had published algorithms which actually, well, it doesn't matter now, but they were not as accurate as how this algorithm from Lund is. Okay, so how can we avoid false sharing? This is a typical example. If we want to avoid false sharing, we shouldn't do like this. So, say we have a counter and each thread counts some elements, something. And now this thread increments its element in this array, and what happens? It will invalidate the counters for all the other threads. And how can you do this in the preflow push algorithm or some other algorithm? Well, maybe not a counter, because that might be a thread local variable, but if you have, for instance, an array of queues, then it will be similar to this. So, I mean, this array is for one element per thread then. Okay, and that is typical. That can happen in lab 3, 4, and 6 when you have these two phases of the preflow push algorithm to collect the different work items. Okay, so this should be avoided. Okay, so how can we also avoid? Well, actually, I would like to say one more thing. Can we reduce false sharing by the hardware? That's an interesting question. It is something to think about. Maybe I will ask something about that in the oral exam, but that is not an essential question to be able to answer. Okay, but if you want to, you can think about it. Okay. Okay, so how can we reduce true sharing? Well, we should avoid communication. And how can we do that? Well, we want to make each thread work on data that only that thread reads and modifies. So ideally, we should be able to partition the input. Not only the input, but the data that is being worked on, the data structures, and reduce shared work as much as possible. Okay, and what does that lead to? It can lead to bad load balance. So it's a very complex trade-off, and there is no simple answer how to do that. But what one has to do is to think deeply and measure and improve the implementation based on measurements. Okay.